Hello everybody. Today's video is about the geographically weighted random forest in R case of high density distribution. And in this case we use adaptive bandwidth, so we have to set the kernel to adaptive instead of fixed. So an adaptive bandwidth ensures that each local forest is built with the same statistical power, number of neighbors, regardless of how crowded the area is. So here is so we need to set geo.weighted to true to apply a weight to the neighbors based on their distance from the focal point, ensuring that even within a dense cluster the closest points have more influence. So additional tips, we have to start with small number of trees, so from 50 to 100, and then increase, and always use the end threads, the multiple core, to help you run faster, because it's computationally expensive. Here the size of the data is about 1000, while for the uniform distribution even 100 it's okay, we can run, but here has to be higher. So for this video, for instance, the data is about 1000, it's more than 1000 observation. So in R it's still the spatial machine learning, the library that is used to perform the geographical random forest. And this is how you install it in standard package from remote or from dev tools. I tried to install it from package here, but it is not. I didn't see it among the packages. So let's come to R and start working. Along with spatial machine learning, we need a spatial feature and a team up as libraries. Okay, so you install them, packages, then you load them. The next step is to load the data set. So make sure that everything runs here. Okay, now this is data set. Let's take the summary of the data set. Summary my data. So this way to have the coordinates, longitude, latitude, then we have depth, this is the well, and the well, the pH is measured along with the sulfate nitrate temperature. So here our dependent variable is pH, and the temperature and depth of the well are our predictors. So let's go to the dimension. Dim my data. So we have 1311 observation. With 100, it did not work. You cannot run. Okay. Then you try to get into optimal bandwidth search, you'll get into trouble. It rejects because of the size of the data. So now let's define our coordinates. Calls to my data brackets command C. So we have a vector of the coordinates x coord and y coord. Okay, so this coordinates. Okay, let's see. Oh, let's have head. Okay, so x coordinate, y coordinate. Now, step 3, we have to split the data set into training and testing. Okay, so still, let's say 80, 20% split. Okay, so we have our sample IDX equal to sample this number of rows in my data comma 0.8 multiplied by number of rows my data. Okay, and then training data equal my data sample IDX. Let me run first. We are testing data, test data equal to excuse me, my data minus sample IDX. also need the coordinates. So training coordinates, so train called equal to calls sample IDX, come on. Test cards equal to cards brackets minus sample IDX cards minus sample IDX. Testing coordinates. Okay, that's dim with train data. Let's verify. Okay. Of train cards. Okay, good. So now we are going to search the optimal bandwidth. So step 4. Excuse me. So best bandwidth equal to geographical random forest dot bandwidth parentheses and the formula equal to pH delta depth plus temperature. Data set equal to train data calls equal to train calls. You can use the whole data set here instead of training. So data set all my data, calls equal calls, and so on. But you know that's going to take time here. The kernel equal adaptive. And then bandwidth dot min equals 20. That's minimum nervous to test. Bandwidth dot max. That's 100. That's maximum neighbors to test. then step equal to 10 in this increment, search increment. Okay, and we run. But from my experience with 1000 data, it generally takes about an hour. So we are not going to wait for an hour. We run, and I will continue with that. Let's run it, and then we print. So it's running. It means that there is no mistake in the file, yeah, in this code. So, but it's going to take for a while. So best bandwidth dollar best might be W capital letter. Okay, so we are going to continue with the training. Sorry. Step 5. Training our geographical or random forest model using the training dataset. Excuse me. So geographically weighted random forest model equal to formula equal to pH delta depth plus temperature plus T. No. We need a GRF here. And then the frame, the data frame equal to train data. Bandwidth we are going to take 80. That's from what I got in my experience. So kernel adaptive coordinates and chord and B3 equal 100. That's number of trees. Forest set to true. it. So also to true. So once it's especially weighted. And then the end thread, go to parallel, and follow the tech colors. Here let's use multiple colors. Okay, so I'm going to stop the bandwidth search. We already have the ATI into this here, but yeah, for the sake of time, I just stop here. It's running, it means that the code is okay. So we'll stop it. Then the run our training model. Let's see. Let's see. Okay. Still, let's type the code for the model evaluation. No, model performance evaluation. Okay. I generally proceed to compare the training performance to compare the two training the testing performance. So start with the training data set, the training metrics. For this we need the prediction on the training data set. We predict on the training to get its performance. So training weights equal predict the GRF for our model DWRF underscore model, the train data, index var dot name equal to export x coordinate and then y coordinates. Local local.w equal to 1 and global w equal to 0. So it's still running, so I have to wait. So then why? Let's continue typing. So let's say 1 here is training. 2, I'm going to, we need the actual pH. This is going to give us the predicted pH, but we need the actual pH from the training data. So we're getting the actual values of the pH from the training data set. You can call it pH actual or train actual, equal to train data pH, train data $pH. And then 3, compute the matrix. The first metric is the R square. Training as R square from 2 1 minus parenthesis sum of parenthesis twice train actual minus train pets squared, and then divide it by the sum of again double parenthesis here, train actual minus mean of that's 1 parenthesis train actual. And then that 1 2 parenthesis here squared. Okay, so already finished here. So calculation time takes 6 minutes. Okay, that's the size of the data. Please roll here. So you have the information here you need about the global model and the local model. Okay, so now you can make the prediction and run here. Forest looks so it's okay. Like color instead of chords, that may cause a problem. Okay. to printing, print, train R2, have the training, root mean square error, train RMSC equal to the square root of the mean of here double parentheses train actual minus train paths and the squared. So, okay, we can go ahead and run. Let's print it here. Print train RMC. Excuse me. So go here, get our train actual, and then we run the train R squared. We print it. It says 92%, and then the train RMC. We print 0. It's 0.16, and then we have the training mean absolute error. Train MAE equal to mean of absolute value of train actual minus train rates. Okay, and then we print it. Okay, point 10. So it shall be this testing matrix. So the prediction test paths testing prediction. So test rates equal to predict the GRF of GWRF model of test data. We have our coordinates x dot var dot name equal to x code, comma y dot var dot name equal to y code, so the code, and then local w equal to 1 and global w equal to 0. Here also we needed actual values of pH. So let's call it test actual. Test data dollar pH. We extract it here. Then outputting testing matrix. So test R squared test R2 equal 1 minus parenthesis sum. Okay, it's finished already, right? Sum of parenthesis test actual minus test spreads squared divided with the sum of test actual minus mean of test actual. Squared here. Okay, let's get our test actual and run our test R squared and then we print it. About 28%, no, about 18%, sorry. Okay, and then we have testing what means more test R and ICE equal the square root of the mean here double parenthesis test actual and the spread squared. And then we print it. Have testing and absolute error test LAE equal to the mean of the absolute value of the difference, mean of the absolute value of the difference between the actual and the predicted pH. Okay, that is, and then we print it. Okay, let's have the summary table for the performance. Okay, perf summary equal to data dot frame parenthesis. We have the matrix, so a vector for the matrix equal to C. Okay, that's R squared. And then RMSE plus codes, then MAE. Okay, come on. Training equal to the vector of its matrix, so train R2 train RMSE and train MAE. Also type testing equal to the vector of its matrix, so test R2 test RMSE and test MAE. Okay, that's when we run it and we print it. There, summary. Okay, this here you have your matrix. The first column, second column is training with its matrix, and the testing is with its corresponding matrix. Now we are going to see the comparison between the two. Models, not matrix here, models. Performance comparison. Try to compare. Okay. Let's call it D. For this you need to have a function. Create a function for this purpose. So let's call it a compute matrix, the name of the function, equal to function actual predicted. Then have curly brackets here. So let's R2 equal to 1 minus the sum of double parentheses actual minus predicted all squared. Then into parentheses here we divide by the sum of double parentheses again here, actual minus predicted, actual minus mean of actual. And then after two parentheses squared. So this is R2. And RMSE, so basically we put the formula how you get this matrix here. So RMSE equal to the square root of the mean of double parenthesis actual minus predicted squared. And then MAE equal to the mean absolute value of actual minus predicted. And then we return a vector of R2 equal R2. So factor R2 here equal to lower R2, RMSC equal to lower upper RMSC equal to lower RMSC, and the upper ME equal to lower ME. Good. That's step 1. Step 2 here is calculating and computing training testing sets. Testing results. Let's create that one. So we have training results equal to our function count matrix train actual function here. Okay, find result of complete matrix. Let me see. Natural. No, it's not minus, it's comma. Sorry about that. Comma. Okay. Yeah, test results. Equal comp matrix. Test actual. Test grade. Okay. Now we need to move the two. Merging into a table. Let's call it comparison table. Equal to data.frame. Parenthesis. Matrix equal to names. Parenthesis. Find results. Comma. Training equal to as dot numeric as dot numeric parenthesis train result comma and the testing equal to as my numeric test results. And then we run the comparison table. Okay, now step 4 is to add the difference, a column for the difference. So let's call the comparison. Excuse me, sorry. Comparison table, dollar, gap, underscore, percentage, equal to the absolute value of double parenthesis here. Comparison table. Training in capital letter minus comparison table dollar testing quality. Divided by comparison table dollar training multiply by 100. Okay. Now we print it. And the complementary. Okay, so you have the matrix, you have the training, corresponding matrix, the name of the matrix, the training, the test, corresponding matrix, and you have the gap between them in percentage, the percentage. It helps you to compare. Okay, now we are going to go to the visualization. Okay, so we take some visualization points. Then this should be the 0.7. So we will from this 0.7 visualization. So visualization, one of the most important is the actual versus predicted. This is scatter plot. Actual versus predicted. Plots. For this we need two libraries. Plot 2. And patchwork. Patch PATCH patchwork. This for the side-by-side plot. And for this purpose, again, we need a function. Function create the plot. Excuse me. We call it performance plot. Performance plot, geographical random forest performance plot. Okay, so function equal to function parentheses actual predicted pattern. Then we have color brackets. close our df data frame equal to data dot frame parenthesis actual capital A equal to actual with lower a, predicted with capital P equal to predicted with lower p. Okay, this is the data frame. And now let's see the G plots. In the plot, we have our data frame AX x equal to actual, y equal to predicted. Plus geometry point, parenthesis alpha equal to 0.5, color equal to steel blue, plus geom AB line intercept equals 0, slope equal to 1, line type equal to dash, and then size, color equal red, size equal to 1. Plus we check geom AP line intercept 0, slope 1, type dash, color red, size 1, plus steel blue, color alpha 5, steel blue, color for the geom height. Okay. Okay, now labels. Labels. In the labels we have title, which equal to the title, comma. Then you have subtitle equal to paste to parentheses, quotes here, I have r square, colon, after the quotes we have comma, and we have round function, and this is the formula to determine the r squared, so minus sum. So this is this function is about the r square performance. So sum around 1 minus sum 1. Okay. parentheses here, and minus parentheses sum of double parentheses actual minus predicted squared divided by sum of two parentheses again here, actual minus mean of actual. And the one, two parentheses here squared, one, two parentheses comma, then three, one, two parentheses after three is a comma, then have x, come back x equal to predicted values after the dot comma, come back to the line, y equal to no, sorry, x actual values and the y equal to predicted values. Sorry about that. Okay, then after the parentheses plus team minimal parentheses team minimal, and I hope the curly bracket is closed. Yes, it's here. Okay, so let's run the function. Okay, good. Now we are going to generate plots. One, creating a function to plot generation. Okay. Training plots. Let's call it fig 1 or plot 1. Plot 1 equal to our function graph underscore perf underscore plot parenthesis trend actual comma trend threads comma encode training performance. Run testing plot. test that underscore plot. And then we have test actual. Test credits. And then in quotes, testing performance. That's underscore performance. And then merging the two plots. Plot 1 plus plot 2. Oh, may take time. I have a lot of data. Okay, this is what you have here. Okay, training performance, testing performance with the R scores. So we see here 93, almost 93. The line of best fit here. Here is cutter. Okay, now we got the special dimension to the plots. Okay, let's have training data on training data. No, you want to add the longitude. So x coordinates. So data plots. You have train data. Ax, As, parentheses, x equal to this train actual. One equal to train rates. And then color, you want the colors to, the color is going to be x coordinate. So the longitude x coordinate. Okay, plus geom point alpha. Let's take 0.7. Alpha 0.7. Let me take here. Plus geom AB line. Geom AB line intercept equal to 0. Slope equal to 1. Line type equal to dash. Plus scale color gradients. Scale color scale underscore color underscore gradients. for the vector C, we just do it like this, plus labels, parentheses, we have title equal to testing performance, so training. Performance colored by longitude. Come here and the color equal to longitude with capital R equals. Then open parentheses, we convert the line, have 10 minutes. Okay, here we are. It's running. Then we do the same thing for the latitude by latitude this time. Okay, so we see here longitude, and we see how they perform. It's the line of best fit. You see where the color down. So low around 16 degrees, that's the best. I think from 15 to 16 the line close to, and here also below, so you see the points here, but the points that are really on the line are in between 15 and 16. Here is a little bit, at 14 is a little bit, here also. Okay, so by longitude you see how your model perform on training. Okay, latitude, you can just copy this and change wherever you have longitude by latitude. So here's going to be y coordinate, nothing change. Here by latitude, here latitude, latitude. I think this is okay. Okay, that's latitude. Look at the training performance. That's the R squared by latitude. So latitude, you see the higher latitudes except from 14 to above 15. And these also, you know, below 13 also. Yeah, here is just on the line. Below 13 is good. Okay, so that's how you see the performance colored by latitude, conformance colored by longitudes. So here, that's on the training data. If the one on testing data, you just copy all this here. I don't like copying pasting, but yeah, for the sake of time, for this video, you just do it. So here we change testing, and wherever you have train, we change it by copy here, test action, test pads. Everything is the same except here. Testing. I think so. That's fine. That's the only thing we need to change here. Here as well. Test. 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 Okay, so run this first longitude, testing performance by longitude. Oh, you see, on the training it was better. It's close all of them, 92%. Now they're scattered away. You see which ones are closer to the line of best fits, lower latitude or lower longitude or higher longitude. Lower 14, below 15, around 14, they're really close. Some just on a mixture. And the medic here is a little bit far. And here 17. Okay, so you analyze and describe. Yeah. Then this is by longitude on the testing, and this is latitude. Okay. Let's see. 14. 0 here, the points around 14, darker around 12. Which ones are closer to the line of best fit? No. And which ones are farther? Okay, so let's see how you plot, you analyze. And what else do you need for this? We already did the spatial autocorrelation in the previous video about the uniform distribution. It's the same, almost the same. It doesn't change. Okay, let's do it with the feature importance, the local feature importance as well, and the interaction this time. Okay, let's go to the feature importance. Variable importance, variable local importance, or feature local importance. Okay. So we need both of them. We are not going to plot that. Let's see for both variables. You already did that. let's call it extracting. Local importance. Extracting the local. For both level. Local importance. Equal to as dot data dot frame as dot data dot frame. We have our model. Geographically weighted random forest model, and from it we extract so dollar local dot variable dot importance. It's dot here instead of point. So instead of the superior sign greater or greater than sign. So here again a typo, local. Okay, and do you run? And then you find the head. Let's have the head of our local importance, not all. The folders. Okay. So for def and the T. Okay, let's see the interaction, because the others we already did in the previous videos. Want to do something novel in this video, not repeating the same thing. But let's see if we don't get the local interaction. I am obliged to go back to the individual importance of the features. Local interaction effect. For this also we need the library ggplot. So you already ran it, but just an information. So if you want to do this library is needed. We need the actual temperature, because you have two values here. So you have two variables here. You have depth and the temperature. So let's we need to extract actual values of temperature from the training data. Okay, so let's call it T actual equal to train data dollar T. We need this. Okay. We also need to convert data frame. Into the special feature object. Okay, so train data SF equal to st plus SF train data equals equal to the vector of x coordinate and y coordinates and the CRS coordinate reference system equal 4326. Okay, we need this also. We need the def local importance. So train data SF dollar def underscore importance equal to our model dollar local point variable point importance dollar def. Let me verify here. Local point variable with upper capital V, capital L, capital V, capital I, and dollar def, dollar here. Okay. Okay. If you need temperature, T, local importance. Train data dollar S, train data SF dollar T importance equal to the model dollar local point variable point importance dollar T. So let's hide extract. This is not our purpose, so we don't need to print here, but we need to extract them for the next step, which where we are now, on which we are now. So this is the interaction plot, plot train data SF. AES X equal to actual T actual temperature actual, so T actual. And Y equal to depth importance. Okay. Plus jump point and jump point for alpha 12.3, plus jump smooth parenthesis method equal to less. Plus labels, levels title, let's say does temperature influence the importance of depth? Or you can flip, does depth influence the importance of temperature? Let's run and see. Okay, you have temperature here, actual temperature, and depth importance one by. Or you can say how does T influence the importance of, how does temperature influence the importance of depth? If you flip, it's going to be how does depth influence the importance of temperature. So it's how does, okay, question mark, it's a question, or exclamation mark, exclamation point. Okay, so we are basically at the end of this video. There are other points, but yeah, I prefer to stop here. If you want to extract these values, they are here. Depth importance is here. T importance here. If you want to plot them, you refer to the previous video. Did that. You plot the local importance of depth and the temperature. And if you want to do the special autocorrelation, you refer to the previous video. It's there. You would have your morals printed. It's yeah. So this is the end of this video. I hope some of the points here would help some people who are doing research using the geographical random forest. So thank you very much for watching it.